See, the screen is sharing with you all?
Yes, ma'am.
All right. It says the ground state energy of hydrogen atom is minus 13.6 electron volt. Even it was not mentioned, you all must be remembering this value. So the first part asks us, what is the kinetic energy of an electron in the second excited state? What is meant by second excited state? What is the value of n?
3.
3, because the first excited state is at n equal to 2. Okay, so let us calculate first the kinetic energy. So see, if E1 is minus 13.6 electron volt, this much. So E3 will be what? What is the general formula for energy? How do we calculate energy? In terms of electron volt for n number of shells.
Minus 13.6 by n square electron volt.
By n square, correct, by n square. So see, if it is by n square, this means E1 will be divided by whatever is the value of n. So if we have third excited state, it means E3 n is equal to 3 for the third excited state. For the third state, that is the second excited state. So E3 will be this E1 divided by square of 3, that is n square. So E3 is minus 13.6 divided by 9. Do you all remember all these values? I think at least till E3 you should remember all the values. E3's value is minus 1.51 electron volt. So you should remember value till E5, n equals to 5. E1 is minus 13.6 and so on. You should remember E2, E3, E4 and at least till E5 because it helps to make the calculation easier. Now see, this is the value of E3. So kinetic energy in the second excited state. Kinetic energy will be the negative of whatever is the energy at the third excited state. If total energy is minus 1.51 electron volt, then kinetic energy is negative of the total energy. This means minus 1.51 with a negative sign. That gives us plus 1.51 electron volt. This is for the first part. Understood?
Yes, ma'am.
Okay. Now see, the second part says that what is the potential energy of an electron in the third excited state. So Abdullah, you won't say. Amalia, you tell me. What is the value of n for third excited state? Yes, Amalia.
Teacher, can you repeat the question?
For the third excited state, you can see on the screen the second part. What is the value of n, number of shell that we take? Will it be 3?
Yes, teacher.
Anyone else? Is she correct? Will it be n equal to 3 for third excited state?
Ma'am, it should be 2, right?
N equal to 4.
It will be n equal to 4. Yes, Mariam, you are also right. Yes, Anya, n equal to 4. See, first excited state is what? First excited state is when you get n equal to 2. This is the first orbit. This is n equal to 1. Then we have n is equal to 2. So electrons will be excited from this to this, from the ground state. This n equal to 1 is known as the ground state. So electrons will be excited from the ground state to the next higher state, that is 2. So that's why this is our first excited state. Then after this, after getting the first excited state, there will be another level that is n equal to 3. So from the first excited state, the electrons will be excited to the next high level. higher level. That is n equal to 3. So n equals to 3 becomes the second excited state. So that's why one excited state becomes higher when we are talking about the excited state. So the way we have done the first part, when we were considering second excited state, this meant the third level, third orbit. Now when we are considering the third excited state, this means from the third shell, the electron has been excited to the fourth shell. So that's why we take the value of n as equal to 4. So n will be equal to 4 and energy will be minus 13.6 divided by square of 4. So this gives us minus 13.6 divided by 16. And this value is minus 0.85 electron volts. So this is the total energy, because this formula, minus 13.6 electron volts, this formula is for the total energy. The relation between potential energy and the total energy you all must be knowing. That is, potential energy is twice of the total energy. So if I have to calculate the potential energy for the third excited state, this means n equals to 4. N equals to 4 is the third excited state. So simply I have to double it. So this will be 2 multiplied by minus 0.85 electron volts, and this gives minus 1.70 electron volts. Understood?
Yes, ma'am.
Now, see the third part. It says if the electron jumps to the ground state from the third excited state. See, when we are considering ground state, Sanya, you tell me, what should be the value of n when we are talking about the ground state? Yes, n will be equal to 1. Correct. N will be equal to 1. Okay, Faisal, you tell me, what is the value of n for third excited state? Yes, Faisal, are you there?
Yes, ma'am.
Yes, what should be the value of n, that is number of orbit for the third excited state?
Ma'am, it will be minus 1.5. 1.
N, value of n.
For the third excited state.
Yes, what should I take? N equal to 1, n equal to 2, n should be equal to 3.
4.
Why 4?
Because excited state is like
One level
plus
higher.
1.
Yes, correct.
Yeah.
Because an excited level, this is one level higher. So now it says that electron is jumping to the ground state from the third state. Means from the third excited state to the ground state, the electron is moving. So third excited state is n is equal to 4, and the ground state is n is equal to 1. So the electron transmission has been occurring from n is equal to 4 to n is equal to 1. So see, E4 we have already calculated, that is minus 0.85 electron volt, and E1, that is the first level, is also already given in the question, as well as we know the value also, that is minus 13.6 electron volt. So we have to find out the wavelength of the emitted photon. The question is asking us to calculate the wavelength of the photon emitted. So see, for finding out the wavelength, first we need to find out the energy, because we know a relation between energy and wavelength. So see, the net energy, the total energy will be simply E4 minus E1. This is the energy difference when the electron is jumping from the third excited state to the ground state. That is the first state. So this will be minus 0.85 minus, and then electron first value of the energy, that is minus 13.6. This is E4, This is the minus sign of the difference, and this minus sign is of the energy of the first state. So this becomes minus 0.85 plus 13.6. That gives, this will be 12.75 electron volts. This will be positive because 13.6 minus 0.85 is there. Now see, in order to calculate the wavelength, let us first convert it into joules only. So yes, Abdullah, you remember, I've told you in the last class also, how will we convert this into joules?
Yes, ma'am. By multiplying 1.6 into 10 to the power minus
Yes,
19.
right. So if we multiply 12.75 into 1.6 into 10 to the power minus 19, this much amount of energy we'll be getting in joules. So if we know the energy, so Mariam, you tell me, what is the relation between wavelength and energy? Yes, Mariam. Mariam, are you there in the class? There is no response from your side. Okay, Fatima, you tell. What is the relation between energy and wavelength? Yes, Fatima? Type it in the chat box if you're unable to unmute yourself. Yes, anyone? What is the relation between energy and wavelength?
E is equal to hc by lambda.
E is equal to hc by lambda. Yes, inversely proportional, but yes, Fatima, inversely proportional, but the constant include hc also. Yes, Abdullah. So E will be equal to hc divided by lambda. So only lambda is unknown and rest of the terms are known. So wavelength will be hc divided by the energy. So wavelength will be 6.6 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by the energy that is given. That is 12.75 into 1.6 into 10 to the power minus 19. This much meters. Clear?
Yes, ma'am.
All right, just note down this question.
Done, ma'am.
Yes. Done?
No.
Yes.
Abdullah, were you having any doubts?
No, ma'am.
Oh. Have you written it down now?
Yes, ma'am.
Let's discuss another question then. See, you all have done energy level diagram, right?
Yes, ma'am.
Okay. So see, this is also an energy level diagram given of hydrogen atom. This is the ground state, n is equal to 1, then the second state, n is equal to 2, then the next state, n is equal to 3, and this is the last given, n is equal to 4. And these are the energy transmissions that are occurring. Now, what all we have to calculate? We have to find out the transition which results in the emission of a photon of wavelength 496 nanometers. So out of all these transmissions which are given, transition from 4 to 3, transition from 4 to 2, then from 4 to the ground state, then from 3 to 2, then from 3 to the ground state, and then from the second to the ground state, that is 1. We have to find out among these which transition which result in the emission of a photon having the wavelength 496 meters. Yes, 496 nanometers. Now see, for that, first let us find out what all are the energies. So E1 is, how much is E1? We have seen in the previous question only.
Minus 13.6.
Minus 13.6. Yes, right. Electron volt. Minus 13.6 electron volt. So see, E2 will be minus 13.6. See, since hydrogen atom is given, so I'm not considering Z. Otherwise, Z square is also added with this. But for hydrogen atom, we know Z is equal to 1. So that's why we don't need to write Z square. Otherwise, we have Z square also apart from this N square. So see, for second, it would be 4. That is minus 3.4 electron volt. For the third, we have seen 1.51 electron volt. And E4 also we have calculated, that was minus 0.85 electron volt. So you should all remember these values so that you don't need to calculate in every question. Now see, we have to find out a difference which will give us 496 nanometer. So before finding out that, let us take out what is the energy for this wavelength, so that it will be easier for us to check. So if the wavelength is 496 nanometers, so 496 nanometers means 496 into 10 to the power minus 9 meters. So let us find out what is the energy of this wavelength. So E will be equal to hc divided by the wavelength lambda. Hc is 6.63 into 10 to the power minus 34. C is the speed of light, that is 3 into 10 to the power 8 divided by, this is 496 into 10 to the power minus 9. Okay, so since these are in electron volt, let us write this also in electron volt only. So for converting joules into electron volt, we need to divide it by 1.6 into 10 to the power minus 19. So once you will solve this, this answer will come around 2.5 electron volts. When you solve, do the calculations after the class. So when you will see that this is coming around 2.5 electron volts. Now see, we don't know which of these energies will result in 2.4 electron volts. So we have to check the energy difference for each of them. So accordingly, we have to check which one of these will be giving us 2.5 electron volts, because that only will be the energy for this wavelength. That transition will be occurring. So if I take the difference between E4 and E2, these two, that is, if I take the energy difference between energy at the fourth state and energy at the second state. So for the fourth state, it is minus 0.85, and for the second state, it is minus 3.4. So this gives minus 0.85 plus 3.4. So this will be around 2.5 electron volts only. So this means the transition from n is equal to 4 to n is equal to 2 level results in the emission of the photon of wavelength, that is 496 nanometers. Now see, if you take the energy difference between the rest of them, between 3 and 4, 3 and 1, 1 and 2, 1 and 4, this will not come out to be 2.5 electron volts. So we have the answer as energy transition from 4 to second. See, from 4, this is from 4 to the third. This one is from 4 to the second. So this means this wavelength, this is giving us this transition is resulting in the emission of a photon with the wavelength 496 nanometers. Understood? Is this question
Could you
clear to
repeat? Could you repeat the diagram?
Okay, see these, what are these energy level indicating? This is indicating that a transition is occurring. These are all the orbits, these are all the levels of the atom. Now see, this is the first level. It means if this is the nucleus, then n is equal to 1 is this, n is equal to 2 is this, n is equal to 3 in this, and so on, as n is equal to 4 and the rest of it. So these are representing, let's take this. This means from the fourth one. From the fourth one to the n is equal to 3 value. That is when the electron is transiting from this one to this level. This is represented by this. Then for this, n is equal to 4 to n is equal to 2. Means electron is jumping from n is equal to 4 level to n is equal to 2 orbit. So similarly, for this, we have n is equal to 4 to the ground state, that is n is equal to 1. This electron is moving. So whatever theory you have studied, this has been represented in this energy level diagram. Now see, the question asked us which of these will result in the wavelength 496 nanometers. So see, out of these, if I take out the energy for the wavelength of 496 nanometers, I see that the energy for this is coming out to be 2.5 electron volts. So we have to find that transition which results in 2.5 electron volts. See, if you take rest of them, if you take E3 minus E1, or if you take E4 minus E1, these will not be resulting in 2.5 electron volts. So this means what? These energy transitions will not be giving us this wavelength. For this wavelength, we have to find out the energy as 2.5 electron volt only. So the energy transition between 4 to the second is giving us 2.5 electron volt. When we are subtracting it, when we are taking out the energy difference, this is only giving us 2.5 electron volt. So this means energy transition from where? From the fourth to the second one. So you have to check all those. This is emitting from the fourth one to the, this is the third one. This is from the fourth one to which one? This is the second. This is which one? This is from the fourth one to the ground state. So that's why only this wavelength that I've marked with blue color, this indicates the transition from the fourth level to the second level. Is it clear now?
Yes, ma'am.
Okay, so note down this question as well.
Ma'am,
Yes.
what is the answer for the second part? Maximum wavelength.
Okay, we had another part, sorry. So it says which transition corresponds to the emission of radiation of maximum wavelength. See, the transition, we have to check it from this given diagram only. Now see, when you will take out the difference, you can calculate it also, but without calculation, what you can do, without calculating all these, you can see the transition, this transition, that is energy from fourth to the third. This is the minimum value. Whenever you will be subtracting it, you can check it from the values also. If you look at the value of E4 and if you look at the value of E3, when you will subtract this, you will get the minimum value. Because see, this is maximum minus, and this will become minus, minus will become plus. So you will be getting the minimum value. So see, if energy is minimum, what happens to the wavelength?
Maximum.
Maximum. So that's why the energy, I'll write it down only. The transition n is equal to 4 to n is equal to 3. You can subtract all the values and see which energy difference is coming the lowest. So this energy that is from 4 to 3 will be the lowest. This level corresponds to the emission of the maximum wavelength. And why the wavelength is maximum? Because the energy difference is minimum. Fine, Abdullah?
Yes, ma'am.
Yes, have you completed?
Yes.
All right, let's see one more question then. See, which level of doubly ionized lithium, that is Li2 plus, has the same energy as the ground state energy of hydrogen atom? So see, we know the ground state energy of hydrogen atom. We have to compare it with the energy of lithium for the ground state.
Ma'am,
Yes.
ma'am, we have done this question.
Okay, you have done this question.
Yeah.
Let's do then another question. Okay, see another question based on energy level diagram. So see, it says energy level of the atom is shown. For the first part, we have to find out which of them will result in transition of wavelength 275 nanometer. So see, this is the similar question. Now you can tell me the steps. For the first part, we have to find out which of them will result in wavelength of 275 nanometer. So what should I do first? I just have this wavelength.
So first, wavelength into 10 raised to minus 9 meter.
Yes, that I understand. Now the step. This is the conversion of the wavelength.
Then we'll find the energy value.
Energy value, right? So E is equal to h3 by lambda. So energy will be 6.6 into 10 to the power minus 34. Then the speed of light is 3 into 10 to the power 8 by the wavelength, that is 275 into 10 to the power minus 9. This much joules. And again, since all these energy level diagrams, these are given again in electron volt. So we should calculate it here only. So this will be 1.6 into 10 to the power minus 19, this much electron volt. So see, when we'll be calculating it, this will come out to be approximately 4.5 electron volt. You can calculate it later on after the class. This will come out to be 4.5 electron volt. Now see, look at the energy level diagram given. So see, which energy do you think will give us 4.5 electron volt? This is plus 4.5 electron volt that we are getting. This is 0 electron volt. This is minus 2. This is minus 4.
And E4 minus and E2.
Ma'am.
Yes, Abdullah.
From n is equal to 4 to n is equal to 2.
N is equal to 4. This is 4, 3, 2, 1. Yes, Abdullah, which one are you saying? From n is equal to?
From 4 to 2.
From 4 to 2. Reason?
Ma'am, because the energy difference is 4.5 electron volt.
Right, correct. See, energy at n is equal to 4 is given to us. Energy right now, for this is a random atom that is given. This is not a hydrogen atom. So this is given to us as 0. Electron volt. See, the way we have done it for the previous question, this question, here we didn't know the energy's value. So we, because this was hydrogen atom, so we had calculated all the values, E1, E2, E3, E4. See, right now in this question, all the values are given to us. This is 0 electron volt, this is minus 2 electron volt, this is minus 4.5 electron volt, and this is minus 10 electron volt. So you think which difference can give us this number as positive? See, definitely 4.5 will be involved. But see, in order to make it positive, we should have a negative sign, and the value should also not change. Means the magnitude should also not change. So see, if I write it as E4 minus E2, that is given. So energy for the fourth level, this is given as 0 electron volt. So 0 electron volt minus, now the energy at the second level, this is given as minus 4.5. So see, 0, this is what? This is 0 minus 4.5. So this gives us plus 4.5 electron volt. And that's what we were requiring. So this energy corresponds to the transition which? B. This gives transition B, for which energy will be 4.5 electron volt. Now see this question, which transition corresponds to emission of radiation of maximum wavelength and minimum wavelength? So see, you have all the 4 values of energy. So which energy, what is the relation between energy and wavelength?
E is equals to hc by lambda.
Inversely proportional.
Inversely proportional. So if energy is higher, then wavelength will be
Minimum.
minimum. So look at all these 4, A, B, C, D. We have all the energy values written. So which is the maximum energy? Look at the magnitude of all these energies.
0.
Which one is the maximum? 0 is the maximum.
Ma'am, from n is equal to 3 to n is equal to 1.
No, just look at all these values. The energy values that are given. See, if you look at the magnitude, which one is the greater?
10 electron volt.
10 electron volt will be greater. So see, we have calculated rest of them. So if you consider this transition, that is transition D. So for transition D, the energy emission is maximum. So if energy emission is maximum, then what kind of wavelength will we be getting? Minimum wavelength or
Minimum
maximum
wavelength.
wavelength? Minimum wavelength. And see, similarly for this, from 4 to 3, that is 0 electron volt to minus 2 electron volt. If this transition A, if you look at this transition A, the energy emission is minimum. So wavelength should be
Maximum.
maximum. So for the second part, the maximum wavelength will be for the transition A, because the energy is minimum, and minimum wavelength will be for the D, because energy is maximum. Is this clear? Yes, understood.
Ma'am, could you explain the diagram again?
See, this is similar to the previous one that we have done already. This is, if I say this is n is equal to 4, this is n equal to 3, this is n equal to 2, and this is the first state. Now see, previously what we have seen was for the hydrogen atom. So for the hydrogen atom, we had specific values. That is, for the first level, it was given minus 13.6. For the second level, we had calculated. Then for the third level, then for the fourth level, we had calculated. Now see, this energy level diagram is given of a random atom. So this wavelength, this A transition, represents energy transition from 0 electron volt to minus 2 electron volt. This second transition, that is this B transition, this represents transition from the energy level at 0 electron volt to minus 4.5 electron volt. This third one, this C represents what? This represents minus 2 electron volt to minus 4 electron volt, 4.5 electron volt. Similarly, for the fourth one, this D part, this shows transition from minus 2 electron volt to minus 10 electron volt. This is what is meant by the diagram.
Yes, Sam, is it the last question?
Yes, sir. This is the last one. Yes, written.
Yes, ma'am, done.
Yes, sir. So please continue.
Thank you.
Thank you.
Assalamualaikum, sir.
Walaikum salam. So just give me a second. Yes. So up to last class, we have finished that atomic structure thing. Huh? We have finished Bohr model. We have calculated energy, and we have also plotted that energy level diagram. There's only one small topic left in atom, and that is spectrum. What do you mean by spectrum of an atom? As we have discussed earlier, the way every human being have a specific fingerprints, the fingerprints of every human being is very unique. In the same way, every atom have its specific spectrum. Like the spectrum of no two elements can match. Every element have a signature spectrum. So one example of spectrum is that Vibgyor pattern. That Vibgyor pattern of white light is an example of spectrum. But that spectrum is not for a particular atom. That is for a white light only. But if you take a particular atom, let's say you take hydrogen, that hydrogen will have a very specific type of spectrum. If you take helium, that will have a signature spectrum. Similarly, all elements of periodic table have some spectrum. So now we have to discuss what is spectrum, how we get spectrum, and what are the types of spectrum. Then we will try to explain spectrum using the Bohr model. Yes. So see, what is spectrum and how spectrums are operated. We draw energy level diagram in the last lecture. We draw n equal to 1, n equal to 2, n equal to 3, all these energies. So you all were present in the last lecture, na? Fatma, Faisal, Mariam.
Yes, sir.
You all were there in the last lecture. So if electrons jump from higher energy state to lower energy state, then what happens? They gain energy or they lose energy?
They lose energy.
Okay, Sanya, you were not there in the last lecture. Sanya, for the next 10-15 minutes, you may not get what I'm teaching because Whatever I'll use is based on the last lecture. So when electrons jump from higher energy level to low energy level, it will lose energy. It will lose energy in the form of radiation. And that radiation can form spectrum. This is known as emission spectrum. So when electrons jump from high energy level to lower energy level, they emit radiation of a very particular frequency, for very particular wavelength. That gives emission spectrum. So emission spectrum formed by frequency of the emitted light. And let's say this is example of emission spectrum. Say you take a hot gas, this could be hydrogen, this could be helium, this could be lithium. This gas will emit some radiation. So that radiation, the gas will emit radiation when electrons of the gas will jump from some higher energy state to low energy state. And see, this type of extra spectra you may get. Black color means these radiations are not emitted. Gas have emitted this particular, this color, this color, this color, and this color. Black means absence of any color. So this spectrum is signature for a particular type of gas. We call this as line spectrum because you can see lines of different colors, and in between the lines you have black color. Black color means these no emitted radiation for this particular range. So that's the emission spectrum. And this emission spectrum, and again repeating, it is specific for a particular element. For helium, helium have a specific spectrum. The spectrum of helium will not match with that of hydrogen. It's like fingerprints of human beings. Yes, is this emission spectrum clear? Yes, no,
Yes, sir.
clear. So okay, let's start with you. Mariam, when you get emission spectrum, when electrons jump from low energy state to high energy state or high to low energy state? Mariam, when you will get the energy, this emission spectrum, when electrons jump from low to high energy or high to low energy? No, not in class, huh? Amalia, when we get emission spectrum? Okay, just no, Mariam, I'm sorry. Okay, yeah, high to low. Amalia and Mariam both are correct. High to low. And when electrons jump from high to low, they will emit a particular frequency, and that frequency, we are representing that frequency by color. Now see, what does absorption spectrum mean? Say you take a gas. This is some gas, some cold gas, gas at low temperature, and you take some radiation. You allow this radiation to pass through the gas. When I'm saying is a cold gas, that means all the elements are in the ground state, or electrons are in the ground state. Electrons are in the ground state. So when some radiation passes through the atom, see, this atom will absorb some energy. So when atom absorb energy, or you can say that gas absorb energy, what happened with the electrons? Fatma, what do you think? If you have a gas in which all electrons are in the ground state, if it can absorb some energy, what will happen with the electrons? Electrons will remain in the ground state, or they will jump to some excited states? Fatima. Abdullah. So what will happen with the electrons? They will remain in the ground state, or they will jump to the excited state?
Jump.
Yes, they will absorb energy. When electron absorb energy, they will go to higher energy state, or some higher energy state. When they absorb energy, then one more important thing. Can electron absorb any energy, or it will absorb only those energies which are corresponding to the difference of energy level? Yes, Faisal, what do you think? Can electron absorb every possible energy, or it will absorb only those energies which are corresponding to the difference of energy level? Faisal?
Sir, which are corresponding to different.
So it will absorb only some particular energies which are corresponding to the difference in energy level. Is this statement clear? Electrons can absorb only those energies which are corresponding to the difference in energy levels. So you can conclude that electrons will absorb only those frequencies which are corresponding to the difference in energy level. So electrons will not absorb all energies. Electrons will not absorb all frequencies. It will absorb only those frequencies which are corresponding to difference in energy level. And when these radiation, which have all possible frequencies, passes through this gold gas, this gas will absorb some specific energy. So the energy that this gas will absorb will be missing from the spectrum. Means these black colors shows frequencies absorbed by the gas. It shows frequencies absorbed by the gas. These colors shows frequencies emitted by the gas. Frequencies emitted by gas. So this is what we call emission spectrum, and this is what we call absorption spectrum. Emission spectrum means your gas will emit all possible gas will emit some frequencies, and those frequencies will form emitted spectrum. In absorption spectrum, your gas will absorb certain energies. So from the spectrum, those particular energies will be missing, and those missing energies will form line absorption spectrum. And can you guess any relation between these frequencies, means the lines of the emission spectrum and lines of the absorption spectrum? Can you relate their frequencies? These lines will have same frequencies or different frequencies? Yes, can anyone relate these two frequencies? Frequencies of emission spectrum and frequencies of absorption spectrum. Means these are the frequencies which are emitted by the gas. In absorption, these are the frequencies which are absorbed by the gas. Those frequencies will be same or they could be different.
The same.
Yes, same is the right answer. Why you think that these two frequencies would be same?
Sir, because their energy differences will be say equal to X mu.
Exactly, good. So basically, gas emit or absorb energy corresponding to the difference of energy level. So if energy level is same now, whether gas absorb energy or it emit energy, the energy level is same. So the frequencies of the emission spectrum and the missing frequencies in the absorption spectrum are exactly same. So these are the frequencies that gas is emitting, and these are the frequencies that your gas is absorbing. So these are the two types of spectrums: the emission spectrum and the absorption spectrum. We have to mathematically calculate the emission spectrum of hydrogen atom. We will draw the emission spectrum of hydrogen. Please note it down. It's fully clear. So this is the definition for emission spectrum. Tell me once you have written, come to the next. So in emission spectrum, you can say that electrons move from higher energy state to lower energy. absorption state. They emit some radiation. Can I scroll it?
Yes, sir.
This is for the absorption spectrum. So in absorption spectrum, your electrons will jump from high energy level to low energy level. Sorry, they will move from low to high. In emission, they will move from high to low.
Sir, could you scroll up?
Yes. Yes, can I scroll it further?
Yes, sir.
If you want, you can take screenshot of this or you can draw it. Written? Okay, the next part of the calculation, the last part of the calculation is to calculate these frequencies. So we'll do a calculation to calculate how to calculate the wavelength and the frequencies of these emitted radiation. Like you have to calculate the wavelength of this particular line, the wavelength of this particular line. So first we will do it for hydrogen or hydrogen-like atoms, means atoms having single electron. spectral series of hydrogen will do. Spectral series of hydrogen. So currently we are calculating the emission spectrum. So in emission spectrum, electrons will jump from low energy state to higher energy states. Amalia. In emission spectrum, Amalia, electron will jump from low energy state to high or high to low? This is N2 level. This is some N1 level. This is E1. I'm asking electrons, this atom will emit radiation. So electron will jump from high to lower or lower to higher? Faisal?
Sir, from higher to lower.
From higher to lower. So electrons jump from N2 to N1. And corresponding to the difference in energy, they will emit radiation of certain wavelength lambda. You have to calculate this wavelength lambda. So we can write that energy emitted is E2, higher energy minus lower energy, E2 minus E. This energy we have calculated in the last class, this one. We have calculated this energy. This is the expression of energy. Where is it? This one. K square Z square e to the power 4 2 pi square m by n square h square. This is the expression of the energy that we have to write. So Abdullah, can you just dictate me this expression?
So this one, this minus k square z square.
Yes.
1 second, sir.
Minus of
K square z, k square z e to the power 4 pi square
pi square m.
m divided by n square h square.
Is there any 2 in the numerator? No.
No, sir, there is no 2 in the numerator.
Okay.
Yes, sir, there is 1 2. I forgot that. There is 1 2.
There's 1. Then this is minus of. It's see this is 2, so we'll write n2 here. And this is minus of k square z e to the power 4. It's 2 pi square m over n1 square h. So it will be n1 square h. N1 square h square. We can write this delta E as h nu, applying constant into frequency. So we can write this as minus. So this minus and minus will be plus. So I'm taking this whole term k square. I'm taking this whole term as common. K square will be common. Z will be common. E to the power 4
Sir.
will be common. Yes.
Sir, z square, no?
Is it z square or z only?
It is z square.
It's z square. Z square. 2 pi square m over h square. So you can write this as this is 1 by n square minus 1 by n square. You need wavelength, not frequency. Does anyone remember any relation between wavelength and frequency?
Nu is equal to c lambda.
C, nu is equal to
C
C
by
lambda, C by lambda. So instead of nu, you can write this is hc by lambda is k square z square e to the power 4. It's 2 pi square m over h square 1 by n1 square minus 1 by n2 square. So you can get the value of 1 by lambda from here. It's k square z square e to the power 4 2 pi square m by c h cube into 1 by n 1 square minus 1 by 2 square. See, if you look at this term carefully, so instead of this z, everything is constant. Means instead of this z, this whole term is constant. And we call this whole term as RH, which is Rydberg constant. We call this as Rydberg constant. The value of Rydberg constant is, it's 1.09 into 10 raised to the power 7 meter units. So in terms of Rydberg constant, you can write that 1 by lambda is Rydberg constant, z square 1 by n1 square minus 1 by n2 square. So this is the expression of it. So from here, you can calculate the wavelength corresponding to a particular transition. See, N2 is greater than N1. N2 is the higher energy state, N1 is the low energy state. So if you know high and low energy state, then you can calculate the wavelength, corresponding wavelength. Means if you know that this is 3, this is 1, then you can calculate the wavelength of the light emitted. And this wavelength is the same wavelength that I was plotting here. This is the wavelength. If you need this wavelength, you should know what was the higher energy level, what was the lower energy level. If you know higher and low energy level, then you can calculate this particular wavelength using this relation. Note it down. Then we will study different types of series. See, this is one of the most important part of atomic structure. Yes, can I scroll it?
Yes, sir.
Written? Okay, next. See, if we fix this N1, which is the lower energy level, then we can have different types of series. That first one is the Lyman series. Okay, Sania, out of N1 and N2, which one is the lower energy level and which one is the higher energy level? Sania, out of N1 and N2, which energy level is the lower energy level and which one is the higher energy? N2 is higher and N1 is lower. So if I fixed N1 equal to 1, low energy level is 1, higher could be any 2, 3, 4 or any. So if electrons are moving from any higher energy state to the ground state, then the series that we get is the Lyman series. So when I'm saying Lyman, that means I'm calculating for hydrogen. For hydrogen, I will put Z equal to 1. Atomic number of hydrogen is 1. So when I put H equal to 1, I get its Rydberg constant 1 by 1 square minus 1 by N2 square. 2, 3, 4, it will go up to infinity. So if I ask you to calculate the first line of the Lyman series, then for the first line of Lyman series, your N2 will be equal to 2. So if you want to get the first line, you will write it 1 by lambda 1 is Rydberg constant 1 by 1 square minus 1 by 2 square. So get 3 by 4 or Rydberg constant. That's the Lyman series. This first line is sometimes known as alpha line. If someone asks you to calculate the alpha line, that means the first line. So if you wish to calculate the second line of Lyman series, if you want second line of Lyman series, then put N2. Then what would be the value of N2, Fatima? For the second line, what would be the value of N2? Fatima Fida. You're not in class, huh? Mariam. What's the value of N2 for the next line of this Lyman series? Yes, N2 will be 3. So you can calculate the next line, which is 1 by lambda 2, which is RH. 1 by N1 square, not even N1 is 1. 1 by 1 square minus 1 by 3 square. Okay, if I ask you to calculate the last line, for last line, your N2 will be infinity. So we'll write this as 1 by lambda infinity is RH. It's 1 by 1 square minus 1 by infinity. First one is Lyman series. First line of Lyman series, second line of Lyman series, and the last line of Lyman series. So, can anyone tell me which transition corresponds to the line of maximum energy difference? In which line the energy difference is maximum? See, this is the transition from n equal to 2 to n equal to 1.
This is the transition from n equal to 3 to n equal to 1. N equal to 1. And this is the transition from n equal to infinite to n equal to 1.
So last line.
The last line will have maximum energy difference. And when energy difference is maximum, that means your wavelength will be minimum. You can write your energy as hc by lambda. So energy and wavelength are inversely proportional. So when energy difference is maximum, the wavelength is minimum. So here in this line, in this particular line, your wavelength is lambda minimum. It's a minimum wavelength. Because the energy difference is maximum. Here the energy difference is minimum, like 1, 2 to 1. So yeah, here the wavelength is maximum. So you also have to remember like which transition corresponds to the maximum wavelength and which transition corresponds to the minimum wavelength. So the transition from 2 to 1 corresponds to the maximum wavelength, and the transition from infinity to 1 will correspond to the minimum wavelength. The last term that one should remember about the transition is it will lie in the UV region, ultraviolet region. So that is a Lyman series. Means from any higher energy level, if your electron jumps to n equal to 1 level, then this is known as Lyman series. So 1 by lambda is RH 1 by 1 square minus 1 by n2 square. For Lyman series, n2 is 2 and n1 is 1, then n2 is 3, then n2 is infinite. If your n2 is 2, then it's the smallest transition and your wavelength is maximum. From infinity to 1, this transition corresponds to maximum energy difference and your wavelength is minimum. Similarly, we can define different other transitions, other type of series also, Balmer, Paschen, bracket. But first of all, just note this Lyman series, then we'll do Balmer series.
Sir,
Yes.
so what is this first line, second line, and
First line, second line means see. Or just give me 1 second. I'm drawing a diagram here. I will show you. I'm just drawing a diagram that will show you what this first, second, third line is. Just note it down, then show you this diagram. The second line is sometimes known as beta line. Third line is known as gamma line. You should know these terminologies. We're asking you to calculate H alpha line. That means they're asking about the first line. H beta line means the second line of the transition. Noted?
Yes, sir.
So Faisal was asking what this transition means. So Faisal basically just noted this also, that this will lie in UV region. UV means ultraviolet region. Huh? This will lie in ultraviolet region. Ultraviolet region. This will lie. What this first, second, and third line mean? See, let's take a this is the nucleus. Around the nucleus, you have different energy levels, orbits. This is n equal to first orbit. Then you will have second orbit. This is the second orbit. Then you have third orbit. Then you have another orbit.
Sir, shall we draw this?
Sorry?
Shall we draw this?
Yes. Then you have another orbit. So we get 1, 2, 3, 4, 5. We need one more orbit. So see, we have n equal to 1, n equal to 2 orbit, n equal to 3 orbit, n equal to 4, 5, 6, and then last is n equal to infinity. So in the Lyman series, your electrons are, the transition is from higher energy level to n equal to 1 level. Means this particular talking about this transition. We are talking about this transition. We are talking about this transition, and this transition. All these transitions are in the Lyman series. So when I say the first line, that means from 2 to 1. The next transition is from 3 to 1. The next is from 4 to 1, then 5 to 1, then 6 to 1. Is it clear, Faisal now?
Yes, sir.
This Lyman. And this one, this is the transition which have the minimum energy difference, means the maximum wavelength. And the last transition will have maximum energy difference but minimum wavelength. That's the first series. The next series is known as Bahrain series. So when we talk about Bahrain series means it will have N1 is 2 and N2 is 3, 4, 5, it's up to infinity. So if you have a transition from any of the higher energy state to n equal to 2 state, means you can take transition from 3 to 2, or the transition is from 4 to 2, or the transition is from 5 to 2, or some infinity to 2, then this is known as the Bahrain series. So you can write your lambda as 1 by lambda is RH, 1 by 2 square minus 1 by n2 square. So which transition will correspond to the first line? Faisal? First line
N is
means
equals to 3.
3,
Mm.
3 to 2. This transition will correspond to the first line. So you can calculate 1 by lambda is RH. It's 1 by 2 square minus 1 by 3 square. Okay, this will correspond to the minimum wavelength or the maximum wavelength? Who will tell? Fatma, this transition will correspond to the minimum wavelength or the maximum wavelength? Energy difference is minimum. It will correspond to the minimum or the maximum wavelength. This
Yes,
will
sir.
correspond to the maximum wavelength. See, energy difference is minimum. 2 to 3, the energy difference is minimum. The wavelength is maximum. If you look at here, see, we're talking about this transition 2 to 1. Here, the energy difference is minimum, so wavelength will be max. The last transition, infinity to 2.
Sir.
Yes.
So the formula for 1 by lambda was RH1, you wrote N2 raised to 4.
No, sorry. N2 square. 1 by lambda minimum is RH. 1 by 2 square minus 1 by infinity square. This transition, the last transition where the energy difference is maximum, so wavelength will be minimum. That is Bohr series. And Bohr series lies in the visible region. This lies in the visible region of the spectrum. After the Bohr series, the next is Paschen. For Paschen, we put your N1 equal to 3. Means from any of the higher energy state, if your electrons jumps to N equal to 3 state, 4 to 3, 5 to 3, 6 to 3, any. This is Paschen. So your N2 could be 4, it could be 5 or up to infinity. If I take first line, first transition is 4 to 5. So Fatma, this will correspond, not 4 to 5, 5 to 4. This will correspond to minimum wavelength or maximum wavelength? First transition, 5 to 4. Yes, Fatma, this time wavelength will be minimum or maximum? See, Fatma, just look at this diagram. See it very carefully. This is N equal to 4. This is N equal to 3. This is N equal to 5. This is 3. This is N equal to 6. This is 3. That's the first line. This is the second line. This is the third line. Just tell me which line corresponds to the minimum energy difference. First, second, third. Which line corresponds to the minimum energy difference, Fatima? First line. So when energy difference is minimum, your wavelength will be maximum. We decide in this way. The last transition is infinity to 1. So the last transition corresponds to maximum energy. So what about the wavelength? Wavelength will be maximum or minimum? In the last line. It's coming from infinity to 1. Energy difference is maximum. What about the wavelength? Wavelength will be minimum. Remember this thing. Energy difference is inversely proportional to wave. Is it clear?
Yes, sir.
So here your wavelength will be maximum. 1 by 4 square minus 1 by 5 square. And Paschen will lie in infrared region. Infrared region of your spectrum. This will lie. After Paschen, the next is the bracket. So if electrons jump from any of the higher state to N equal to 4 state, this transition, or from infinity to this transition, then this is known as bracket. Fatma, one last time. Which transition will correspond to maximum wavelength? 5 to 4 or infinity to 4? In bracket, your N1 is 5 now. N1 is 4. Your N2 is 5, 6, 7 up to infinity. So the first transition is 5 to 4. So here wavelength is maximum. And this will be 1 by 4 square minus 1 by 5 square, because energy difference is minimum. If you look at this transition, for this particular transition, this is from 5 energy level to 4th energy level. Your energy difference is minimum, so wavelength is maximum. If you need minimum wavelength, then it's infinity to 4. So 1 by lambda minimum will be RH 1 by 4 square minus 1 by infinity square. After bracket, the next is the last one is the fund series. For the fund series, your N1 is 5, your N2 is 6, your N2 is 7, and it goes up to infinity. So 1 by lambda is RH 1 by 5 square minus 1 by N2 square. If you want maximum wavelength, then the transition is from 6 to 5. Means 1 by lambda maximum will be RH 1 by 5 square minus 1 by 6 square. This is the maximum wavelength. For the minimum wavelength, you need the transition from I need 6 to 5, infinity to 5. Energy difference is maximum, so the wavelength is minimum. 1 by 5 square. So these are the questions that are generally asked in this spectral series of hydrogen. And this also lies in infrared region. It lies,
Bracket also lies in infrared region.
yes, all lies in infrared region, IR region. This bracket also lies in IR region. Do it. Draw this diagram. And tell me once you have written. Just tell me once you have written. Can I scroll it?
Sir,
Yes.
sir, for a question, N1 is 3.
Yes, for partition N1 is 3, right?
Yeah, but in the formula, why did we 4 square?
Sorry. This is first. So it's 3 square minus 4 square. Yes, Abdullah, after this topic class is over. Yes, written. Can I scroll it? Yes, can I scroll it further?
Yes, sir.
It's okay. So that was the last topic of this Lyman, this spectral series of hydrogen. The next topic is limitations of Bohr model. So that is your homework. You will write three limitations, at least three limitations of this model. So this atom is also finished. From the next class, we will start this nucleus. So I'll stop here. From the next class, we'll start with the nucleus. Huh? So, okay. Thank you. Allah Hafiz.
Thank you, sir.